Now we go to another important question, which is why to study solid mechanics or mechanics of material? What are the reasons of studying this subject, which is so important in mechanical engineering, that we study this subject uh, one branch in first year, statics, and then solid mechanics 1 and then solid mechanics 2, and then followed by in the fun year stress analysis. What's the reason? Okay, so this is a very important piece of document. Okay, so mechanics of materials is a study of, as I've already told you in the previous slides, of internal effects caused by the loads which are acting on the bodies, and those loads can be in any form, as I've told you. They can be axial loads, they can be bending loads, they can be shear loads, they can be stretching or twisting. So these are all basically termed as different types of loads. Okay, so what are the internal effects? Why are the internal effects in an object important? I mean, what is the importance of this uh, two words, internal effects? Why it is very important from the load and stress point of view? So we'll explain this. So engineers are called upon to design, and it not only to build design, but to design systems or components that basically are plugged in various assemblies to perform functions that are helpful for the humans, okay, for the society, okay. So whether they are designing automobiles, airplanes, aircraft, structure, bridges, dams, uh, tunnels, etc., 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 machines. Okay, so regardless of the applications, not only you need to design it; those designs should perform appropriately, but those designs needs also be to be safe. Okay, they needs to be safe, because in whatever design you make, whether it's a bridge or it's a building or it's an aircraft, whatever it is, they will be used by humans, and a lot of humans will be using it. Okay, so they need to be safe for performing all the its respective functions, and safe and optimum successful design functioning must address the following three mechanical concerns. So the number one is, these are the three important things: it's the strength, it's the stiffness, and it's the stability. They are very closely related, but if you understand them, they are miles apart. Okay, so it's basically termed as the, when you study solid mechanics, it's termed as the concept of 3S. It's the concept of 3S, which is very important. Okay, so it is called the strength, the stiffness, and the stability. Strength is the object. Strong explains that, tells us about, is the object strong enough to withstand the type of load that it is being designed for. Okay, the load which is going to apply to it, and it means by design load. Okay, and is it strong enough to able to take that load, or it will basically yield, or it will break or fracture. uh, so it will it continue to perform, and the most important thing is, once the load is being applied, will it continue to perform properly under the loading, and it is, if it's a load which is designed for taking fatigue loads or repeating loadings. Okay, a bridge design is one of the examples for it, and any structure that is undergoing a constant repetitive loads. So any design uh, based on solid mechanics must have appropriate and optimum strength. Okay. Otherwise, if it does not, it will basically either yield, fracture, or break. The second most important thing that is being told about us is the stiffness. Okay, so stiffness means, will the, I mean, how strong, when the load is being applied, how strong it will it able to take that load. If it is not, it will basically going to deform, or it will undergo deformations or deflections. And as I told you in my first class, that those deformations and deflections are very important, because any mechanical component or any system which is being designed, it is basically being designed. There are other components are basically casings are all around those objects, or designed objects are there, and all whenever you design one component with respect to other, you have certain mechanical clearances. Okay, so those fits and tolerances are always there. You have studied in your engineering design one. Okay, so if a project is not stiff enough, okay, it has to have some appropriate stiffness. If it is not stiff enough, those clearances and those fits and tolerances, if are not met, it can have catastrophic effects. It can object lead to basically, like in case of an engine, it can seize. Okay, so stiffness plays a very important role. So much that it cannot perform its intended functions. I just told you in case of a piston moving in a cylinder. Okay, if the piston rings deforms because of thermal expansion, it can result in an engine seizure. Okay, your engine will seize. Stiffness plays a very important role. Then we go to another very important point, and it is basically termed as the stability of the components. Okay, of the system, fluid mechanics design. So this tells, will the object suddenly bend? Stability means, will the object suddenly bend or buckle out of shape at some loads which are elevated, okay, very close to the design load, okay, so that it can no longer continue to perform its its intended function it is being designed for. In case of a, you can take an example of a column. Okay, if a column is there and the load on the bridge just exceeds the design load, for example, will that column be able to sustain that load? Or basically it will, what is called as, it will buckle. It will buckle along any mode of, buckling can have many modes of deformation. So you have done a practical in your, I think, solid mechanics one, in which a load is being applied. There are different end conditions, and for a column on which when the load is applied, okay, sometimes fixed, sometimes fixed, and a pin support is there, and sometimes it is fixed and there is no support on the other side. Different modes of buckling deformations exist. So this is another example of stability. So whatever design which is being under consideration, you must take into account, very important, that where you will be designing your object to perform its intended function. That another thing is that it must be performing its on its design limits. It must be safe. Another very important point. And apart from that, it must be beneficial for the society, and it must have three inherent features, solid mechanics design features. And those three inherent features is, number one, the strength, and number two, the stiffness, and number three, stability. So you must understand these three typical aspects very, very clearly: the strength, the stiffness, and the stability. I hope you will from now onwards understand that whenever you are modeling based on engineering mechanics design, based on solid mechanics design, even you, if you based on your machine design or EMD, elements of machine dynamics design, these three features are very important in designing machine elements, machine components. Or whenever you go in your final year, you go for the final year projects, you must always take account of these three features: the strength, the stiffness, and the stability. These are the key features whenever you design any structural component. Okay, so I hope you understand it clearly. Okay, now we go to another very important slide based on the knowledge that we have gathered over here. Okay. Then we go to another very important thing, classification of materials on the basis of the stress strain diagram. Okay, you know, materials can be classified very easily. I think you might have done this type of chapter in your solid mechanics 1, mechanical properties of materials, in which you have studied stress strain curves in detail, how to get basically the elastic limit, the proportional limit, the yield, then the toughness calculations and the fracture points, okay, and UTS, ultimate tensile stress. All these points you have done in your mechanical properties of materials. You might have cited chapter 3 of RC Hibbler, if I'm not wrong. So here you have a stress strain diagram. Okay, if you look at it, the stress is on the or ordinate, and the strain is will be on the abscissa. The x-axis and the y-axis are very critical. Okay, so you could have different types of materials, and these are the curves of various type of generic materials that you might have come into account. This is the most familiar curve with you. Okay, okay, and you know it basically some sort of a ductile material which you can consider it as aluminium or MS. This is basically a ductile material. Okay, if you look at it, this curve, its origin is starting from there, and then basically it continues to perform, and basically this is the fracture point, and basically sometimes this will be like its UTS, and this tells you some sort of a necking has started from here onwards, and and here basically it is undergoing some sort of a yielding. Okay, so you know these points are very important. So after elastic zone, there is a long plastic region, and like from here, if you say from here somewhere here, the yielding is there, and a long plastic region. And what is happening is that stresses are remain comparatively changing very little, but there is a very long deformation. Okay, so this is a typical example of a ductile material. So you must which in which an axial load is being applied, for example, tension is being applied, and basically a deformation is being occurring. Apart from that, just because this is a stress strain curve of a ductile material, but if you go just to the opposite of ductile, or the antonym of ductile, is the brittle. Okay, if you look at this, is the brittle material. Okay, so what you see here is brittle. Best example is, for example, your cast iron. If you look at it, it is an example of a brittle material. Okay, so the concrete, if you look at it, it's also designed for brittle material. Okay, and you know it that might have studied it if you do not know. Brittle material has got a very inherent property. If you look at its stress strain curve, okay, they have basically got excellent compressive properties. Okay, they have got like cast iron, they have got very good compressive properties, but they perform poorly when it comes to tensile force. If a tensile load is being applied on it, so they perform very poorly in that scenario. That is why you have heard that some RCC, reinforced concrete structures, reinforced concrete columns are being there. Why? Because concrete performs poorly in tensile load. Therefore, we basically make it a composite frame, and we introduce iron bars and iron rods into it, just to basically enhance and make its poor tensile properties slightly better. Okay, in case of there is an earthquake, or basically a seismic load is being applied, or loading, or basically building falling, just to make it a more stiff, it will not fail. So this is an example of a brittle material. Then you can another have an example of a strong material. Okay, strong material is this. Why? Because if you look at it, uh, it is not ductile. If you look at it, this is the stress strain curve of a ductile material. Okay, it is not ductile, neither it is brittle. Okay, for example, a wire breaks suddenly. Example, this is an example of a steel, like a stainless steel. Okay, so it's taking a lot of stress, and basically the strains are comparatively less, which means it's taking more stress and the deformations are little. Okay, in case of wires, wires are very long and thin type of a structure. Okay, so they break suddenly. Example, steel. Okay, but there are not much strains. That is why they're saying it is breaking suddenly. So then, because this was strong, ductile, brittle, and then there is another material which are called plastics. Okay, plastic means if you look from here to here, it might be going very much very small elastic, and then there is a huge strains are being generated, and a plastic deformation is there. Okay, so this is basically a very small, it's, you can see it's a very small elastic zone, and there is a huge plastic deformation and a lot of strain, at some, you can say, at a constant stress value there is a huge deformation in case of plastics. Okay, so it's a very small elastic region. So these are like the brittle materials, the strong materials, examples, and ductile materials. I've given an example for a brittle material, like they have given you glass. I've told you concrete and basically our cast iron are examples of your car wheel drums are made up of cast iron. If you on which basically your rear wheels, you see brake drums over there, and which brake shoes get attached and the car is being stopped. Then plastics, you can say a lot of plastics. For example, you have got elastomers, thermoplastics are there, or any generic plastic will follow this type of a stress strain curve. Similar, the ductile material will be following this kind of type of a stress strain curve. Slightly changed from aluminium to MS or something, but its inherent property will be it will have large deformations in, like compared to an object which is brittle. This type of object, if you have got a similar trajectory of stress strain curve, it will be treated as a strong material because there are very little strains and there is a lot of higher taking a lot of stress, but the deformations are comparatively lesser than the ductile curve which is designed for that. So you have to be very much precise in selecting which type of material will best suit for your design, that you will basically be given the task for your future projects, assignments, or FYP. You have to look on all these aspects, and you have to look for the stress strain curve. Any material you do not know its exact properties or material properties, then you have to go and look for its stress strain curve. Because there are, for one material there are many type of alloys, so every specific material has got a specific stress strain curve which you basically get from laboratory testing data. I hope this understood your point very well. Now we go to another very important information. Okay, now there is another thing that just I've told you, the stress strain diagram, and then here is a picture that differentiates between based on your knowledge of stress strain curve. You have a brittle material, you have a ductile material, and some sort of materials which are basically inherent between the two. Okay, so what happens is basically whenever you go for material testing, you like for example, even though if you've got various types of stress strain curves basically acting in your system. Okay, so here's a picture of a material in which you're applying an axial loading, and you know which machines you can perform this test. It is going to be, if you just recall your last year solid mechanics 1 practicals, it will be the universal testing machine. Okay, so on this machine, if you look at it, a tensile load is being applied. Okay, because of this tensile load which is being applied, this will basically deform. It will deform, and just to remind you how we will be able to calculate the deformations. of that material. Yes, the most accurate one will be the strain gauges, but they are very very costly. And the second best option, if you do not have the financial resources, it will be termed as the device will be termed as the extensometers. The extensometers will be used to get the deformation in case of a universal testing machine. And I know it very well that you might have seen those extensometers or the strain gauges being shown to you in our soil mechanics material strength of material testing lab by the lab engineer or demonstrator, how basically the deformations are being calculated in case of a universal testing machine. Okay, the results can be basically it depends upon what type of material using. So if you're using, for example, you're using cast iron. Okay, if you're using cast iron, then it will have a very the cast iron will have a very unique kind of a failure. It will have for example, if I coat do a coating on whether it on a ductile material or on a brittle material, and we do not know. It's directly know it's I say one material is material X and another is Y, and how and show you various samples. So how will you basically be able to perform and tell that this is a ductile failure, this is a brittle failure? This point, if you look at it, this point, this is the point. अगर आप देखें, if you look this point will show you that this flattening of the areas discontinuity is basically an example of a brittle failure. Then ductile failures can be basically semi. It can be fully ductile, complete ductile material, or it can be a semi-ductile material. So if there is basically a completely ductile material, if there is there, in case of an aluminum failure is there, you will have this type of a V-shaped slot is being formed with a very small type of cone, basically circular cone type formed over here. Okay, so this will be a complete ductile material. What if a material is a semi-ductile material? It's a semi-ductile material. Then you can see here over here is basically what you see is two types of there is a cup formed. There is a cup is being formed at those two edges. So this cup will basically tell you that it is a ductile material but semi-ductile compared to the fully ductile material or compared to the brittle material. And these are the points here basically tells you that the cross section is basically getting reduced, resulting into a specific necking formation is be there until and unless complete failure has taken place and the material has basically shown discontinuity within its veins. So you should be able to understand this kind of a failure, a brittle failure, ductile failure, and a completely ductile failure. Okay, so this is a very important slide as well. Just to reminding you of various types of failures that can occur in brittle, ductile, semi-ductile materials, and you know the names of those materials as well. As I just told you in my previous uh, basically slide for the classification of materials which are basically based on the stress strain curve, okay, in which I told you from ductile to brittle, strong materials, and the last but not the least I told you the plastic material which are undergoing a lot of strains, high strains at a very small plastic zone used to be. Okay, so now we go to